In this lecture, we will continue our studies on Lewis structures. We will continue looking at the Lewis structure for water, analyzing it further than we have in previous lectures. But right now, let's start off by looking at the Lewis structure for hydrogen fluoride, HF. The formula for hydrogen fluoride is HF. Hydrogen has 1 valence electron, and fluorine has 7 valence electrons. We connect the dots and we have our Lewis structure for hydrogen fluoride. But returning to the concept of electronegativity, we know that fluorine has an electronegativity of 3.98 and hydrogen has an electronegativity of 2.20. The difference in electronegativity is 3.98 minus 2.20, which works out to 1.78. So the bond is polar covalent. We think of the concept of 2 electrons being placed between the 2 atoms. We consider electronegativity and we say that the electrons will shift towards the more electronegative element. There is not a complete electron transfer. The difference in electronegativity does not indicate an ionic bond. Only if we have an ionic bond is there a complete electron transfer. And since there is not a complete electron transfer, there is a sharing of electrons. Now, since the bond is polar covalent, the sharing is certainly unequal, but the electrons still remain between the nuclei of the 2 atoms. Hydrogen is not completely transferring its electron to fluorine. We should have some way to indicate the electronic state of the 2 atoms in this bond. What I'm saying is, if there was a complete electron transfer, then I would write a minus on the atom that accepted the electron and a plus on the atom that gave the electron. But there's not a complete electron transfer, but there is a unique nature to the bond. The bond is polarized. Now, we have to think of this term polar. Polar means 2 equals but opposites. So we can think of a battery. A battery has a positive terminal and a negative terminal. The strength of the positive terminal is the same as the strength of the negative terminal, but they are opposites in their strength. We can think of planet Earth spinning on an axis. So we'll say planet Earth is spinning as so. If we looked at planet Earth from the North Pole, we'd see that the planet was spinning in a counterclockwise fashion. The planet is still spinning in this direction. If we looked at it from the South Pole, it would appear that the planet is spinning in a clockwise fashion. So when we think of polar, we should be thinking of opposite but equal in magnitude. We have a concept now of a dipole, 2 equals but opposites. So we shall say that what we have with hydrogen fluoride is a dipole. We will indicate that there is what we will call a partial negative charge on the fluorine. In other words, the electrons shifted towards the fluorine atom, and the fluorine atom now has a partial negative charge. Now, my symbol for a negative charge, of course, is just a minus, because an electron we should think of as being a negative charge. But it is not a complete minus charge. It is a partial minus charge. And so we shall indicate a partial minus charge with a lower delta. Well, if we have formation of a partial negative charge, we should also have formation of an equal but opposite partial positive charge. And we will indicate this as a delta plus. Now, you may have seen in previous studies and when we looked at delta electronegativity that the upper delta means change. So we can think of the difference in electronegativity as being a change of the electronic state of the species in the molecule. In this case, we've already used delta to indicate change, and so we will use the lowercase Greek delta, which also means change. And in this case, our selection of this means that there is a change in the electronic states around the atoms in the bond, but there is not formation of a complete negative charge. There is a partial negative charge and formation of a partial positive charge. So, when we have two atoms bonded and we have a polar covalent bond, then that means we have formation of a dipole. One species forms a partial negative charge and one species forms a partial positive charge. And HF is an example of a species that has a very strong polarity to its bond. The bond is covalent, but the bond is polar. And we look at this and say, well, that's because the differences in electronegativity are right at the very limit of what we would consider to be a polar covalent bond. Let's go ahead and look at water. Now, we've seen in our previous studies that we should draw water as if it had a bent geometry to it. Let's start off by drawing the water molecule as if it was linear. We know that oxygen has 6 valence electrons. We'll place them in 4 even regions around the oxygen atom. We'll bring in a hydrogen atom with its valence electron and the other hydrogen atom with its valence electrons. We connect the dots, make bonds, and then we have our Lewis structure for water. Now, we know that oxygen has an electronegativity of 3.44, and hydrogen has an electronegativity of 2.20. So the difference in electronegativity is 1.24, meaning that this bond is polar covalent. So there is a polarity between the oxygen and hydrogen. We shall say that oxygen has a partial negative charge and each hydrogen has a partial positive charge. The strength of the partial negative charge on oxygen is twice the strength of the partial positive charge on each hydrogen atom. We must now return to the mathematical concept of a vector. A vector in mathematics is something that has magnitude and direction. Let's consider drawing an xy axis. We'll say, here's our x-axis, here's our y-axis. And we'll say, all right, let's go ahead and place a line at the origin and draw the line as such. We look at this and say, well, does this have magnitude? Yes, it does. Going from here to here is the length of this vector. The length of the vector could be given a quantitative value, and so that quantitative value would represent its magnitude. How long is the vector would be an indication of the magnitude of the vector. Does it have direction? Yes, the vector is going in this direction. So remember, a vector has magnitude and direction. Let's go back for a second and look at HF. We can redraw this and we shall say H and F. Is there a way to use our Lewis structure to indicate the polarity of the bond? And the answer is yes, there is. What we shall do is we shall indicate the positive end of our dipole by drawing a plus symbol. So we can think of this end of our bond as having a plus symbol to it. We want the plus symbol next to the hydrogen because the hydrogen has the partial positive charge. We will indicate the negative end of the dipole with an arrow. The arrow points towards the atom that has the partial negative charge. So this then becomes a symbol to indicate a dipole. Now we could turn around and say, well, could I indicate the dipole by drawing the Lewis structure and writing a partial negative and a partial positive? And the answer is yes, both of these symbols are correct symbols for indicating a polar bond. In this case, we'd say this is a polar bond, this is our partial negative charge, this is our partial positive charge. This too is a polar bond, our partial negative charge again on a fluorine, and a partial positive charge on hydrogen. We return to our water molecule and we say, well, what do we have here? Let's go ahead and redraw our Lewis structure. And I will say, let's indicate this bond is a polar bond, and this bond is a polar bond. We can look at the symbols for the dipoles and say that those symbols are vectors. They do have magnitude, length, and they do have direction. So we look over here at our vector and say, well, we put our vector on the xy axis. Now I'm going to return to something that should have been in your studies on Euclidean geometry, and that is vector addition. We shall say that we have an xy axis. And perhaps I have several vectors. We shall say perhaps this is vector 1, perhaps this is vector 2, and maybe we'll draw a third vector as well. Let's go ahead and put a vector like this. So we have vectors 1, 2, and 3. And we want to add these vectors to obtain the net vector. What do we mean by net vector? Well, we could say we're going to add something, subtract something, add something, subtract something, and where do we end up after doing our multiple additions and subtractions? Well, our end state, what we're left with, is referred to as our net. So we'll turn around and say, let's take vector 1 and place it on our xy axis. And I will label this as vector 1. So I took vector 1 and redrew it here. To add vector 2 to vector 1, I will take the base of vector 2 and put it on the head of vector 1. So now I have added vector 1 to vector 2. To add vector 3, I'll put the base of vector 3 and add it to vector 2. And so I'll add these together. And I see that I have ended up right here. I'm going to turn around and say there is a net vector, and that net vector goes from the origin to where I ended up after I did my additions. So I'm going to look over here and say, well, let me go ahead and call this vector 1 and call that vector 2. I'm going to make an xy axis and I'm going to add the vectors together. Now these are the vectors within the molecule. And the vectors in the molecule actually represent dipoles. So I'm going to make my xy axis. I'm going to place vector 1 at the origin and draw it. And I'm going to place the base of vector 2 at the head of vector 1. And it appears that I've gone back to the origin. Well, then that indicates the sum of my two vectors is 0. Now what we're saying is that there is no net dipole. In other words, I add this dipole to that dipole, I get back to the origin, and they cancel one another out. But the question is, does this represent the true state of a water molecule? In other words, if we studied a water molecule and asked whether or not it had a dipole, what is the answer? Does it have a dipole or does it not? Well, water has a very strong dipole. So we look at this and say, well, the way I drew the Lewis structure allowed me to indicate the bonds that are polar covalent as having dipoles. I added the vectors together. I got back to the origin, meaning that there is no net vector. And so this Lewis structure as drawn probably doesn't really represent the chemical behavior or the physical properties of the water molecule. We said that a better way to draw the Lewis structure for water was to draw it with a bench geometry. So let's try that and see how it works out. We'll draw a hydrogen, we'll draw oxygen, and we'll draw another hydrogen. And we know, again, that the hydrogen-oxygen bond is a polar covalent bond. We draw the positive end by the hydrogen, and we draw the negative end by the oxygen. And we will draw two of these. We shall call this vector 1 and this vector 2. Again, we will draw an XY axis. We will place vector 1 on our XY axis, and we will place vector 2 on our XY axis. And we see we do not end up at the origin, we end up at the head of vector 2, meaning that there is a net vector for our water molecule. So what I will do is I will place this net vector on the Lewis structure that I have drawn, and the net vector for a water molecule is drawn as so. So by drawing the Lewis structure in this bent geometry, we're able to add the vectors and see that indeed there is a net vector. It's not the best Lewis structure to draw the water molecule in this linear fashion because such a drawing indicates that there's no net vector. It is far better to draw the Lewis structure with this bent geometry because that bent geometry indicates a dipole, and water has a very strong dipole. This dipole gives water unique properties. As we'll study in further chemical studies, we will see that that dipole is responsible for water's behavior as far as its ability to dissolve ionic compounds. So the point of this is, again, that when we're drawing Lewis structures, we should draw them in a fashion that represents the chemical behavior or properties of that molecule. Let's go ahead and look at CO2. Again, we'll place the carbon atom in the middle because it is less electronegative. We'll place the oxygen with its 6 valence electrons, placing the lone electrons towards carbon's lone electrons, which allows us to make chemical bonds. We shall move this lone electron on carbon to the middle and this lone electron on oxygen to the middle, allowing formation of a double bond. We shall move this electron to the middle and this electron to the middle, allowing formation of another double bond. We know that oxygen's electronegativity is 3.44 and carbon's is 2.55. The difference in electronegativity is 0.89. This is between 0.4 and 1.8, so the carbon-oxygen bond is a polar covalent bond. We will look at this and say, all right, well, let's go ahead and redraw our Lewis structure. And I will say that there is a dipole going from the carbon to the oxygen. There is another equal but opposite direction dipole going from the carbon to the other oxygen. I will label this dipole 1 and label this dipole 2. I will draw an XY axis. I will place dipole 1 at the origin, and I will place the base of vector 2 at the head of vector 1, and I see that I return to the origin. So carbon dioxide has dipoles within the molecule. There are 2 carbon-oxygen dipoles within a carbon dioxide molecule. But the carbon dioxide molecule itself is nonpolar. Why? Because the dipoles point in exactly opposite directions and they cancel one another out. We saw with the water molecule, it also has 2 dipoles. But when we do our vector addition, the dipoles do not cancel one another out. Indeed, the dipoles add to one another. With our carbon dioxide molecule, the dipoles do cancel one another out. Thus, our Lewis structures must truly represent the geometry of the molecule. Once we have the true geometry of the molecule, then we can do our vector addition and see if those vectors cancel out. Let's consider ammonia. Ammonia is NH3. We will place the nitrogen atom as so with its 5 valence electrons. We will bring in the 3 hydrogen atoms. And again, we could look at the electronegativities and realize that the nitrogen-hydrogen bond is a polar covalent bond. We could label this vector 1. We could label this vector 2. And we could label this vector 3. We could draw our xy axis. We could place vector 1. We could place vector 2, and we could place vector 3. And we see that there is indeed a net vector. The dipoles do not cancel one another out, and thus the ammonia molecule is a polar molecule. Now, caution must be exercised. We are representing a 3-dimensional object on a 2-dimensional plane, and it looks like these 2 bonds are 90 degrees away from one another. But remember, we looked at the ammonia molecule and we said, well, the ammonia molecule is a trigonal pyramidal molecule, or its geometry between the 3 hydrogen atoms and a nitrogen was a trigonal pyramid. And so we have to ask ourselves, well, is this methodology of adding up the dipoles accurate in this case? So here is our ammonia molecule, and we could look at it and say, well, here's a dipole pointed in this direction, and this direction. And as we look at it, we realize, well, indeed, these 3 dipoles would all add up to a net dipole going in this direction. So there is indeed a dipole that we can see in our 3-dimensional molecule. As we look over here, we would say, well, as I've drawn this and looked at our xy axis, we realize there is a net dipole. And if we drew that net dipole, it would go straight up through the nitrogen atom. We see that analyzing the Lewis structure of ammonia gives us some understanding of the chemical properties of ammonia. Ammonia is a polar molecule. We see that studying the Lewis structure and the dipole properties of CO2 gives us some insight as to the chemical properties of CO2. CO2 is a nonpolar molecule. It does not have a dipole. We look at H2O and we see that H2O is indeed a polar molecule. It has a dipole. Lewis structures give us a way to visualize a molecule. By analyzing the Lewis structure, we can ascertain certain properties of the molecule. We've seen that we can use electronegativity to determine if an atom-atom bond is polar, and we can use the Lewis structure to ascertain if the molecule as a whole is polar. The polarity or non-polarity of a molecule gives that molecule unique properties that we will look at in further chemical studies.